Chennai Mathematical Institute, one of the leading institutions for mathematics. And so he will speak on logic, automata, and program verification.
So I'm, as you can see, a theoretical computer scientist. So what I thought is that though it is recent advances, I thought this would be a possibly unfamiliar area. So I'm going to talk about not so recent advances, just to give you some background on the kinds of things that some of us do. And then towards the end, I will just very briefly touch on what we are looking at now. But before that, I should express my gratitude to Kalyan and Pranav and others who kind of persuaded me to come. So it took a little bit of persuasion, but in the end, I'm very happy I was able to come, and I hope to come more often. Having come here once, very nice. So what is the context? So there are basically three things in the title. So I'll spend most of my time in the beginning on the first two, automata and logic, and then I will talk about program verification. So automata, as some of you may have come across, are very abstract mathematical models of computation. So it goes back actually to the work of Alan Turing. So some of you may have heard of this thing called the Turing machine. So it's not a real machine, it's an abstract machine which tries to encapsulate how the process of computation takes place. So there is some automation in terms of what the machine does. And then you ask properties of what it can and cannot do. And of course, the fundamental result of Turing was there are many things that it cannot do. And then, in particular, a much simpler model, which I will talk about, are these finite state automata. So they are essentially good ways of abstractly defining what computing systems do, because it's very tedious to look at the actual mechanics. So it's the equivalent of building a model, mathematical model of a bridge or a chemical process or something. So this is the equivalent. And the aim is to describe what these computations are doing. So now that in itself is a little bit challenging. In the early days, all computation was essentially numerical. So you could say that this computation is supposed to compute, say, square root or it. So you could say if I give you input n, it should compute square root of n. If it does not, it's wrong. But if I ask you, what is this doing? It's much harder. Okay? Because all the time it's waiting to see if somebody is calling me. It's trying to connect. If it's on the internet, it's trying to connect. So there are many things that are doing which are not in the nature of I give you n and you give me f of n. So for such things, you need a language. And it turns out that mathematical logic is a useful basis for this language. So this is the starting point of this automata and logic. And it turned out that from the early 1960s, that there is actually a very strong and possibly unexpected link between these two. So logic can describe computation as well as automata can describe computation, and you can convert back and forth between the two. And so the original reason to actually look at even Turing's original motivation for inventing the Turing machine was to solve questions in logic. Right? Hilbert had asked, are all mathematical logic formulas computable from axioms, or do we really need ingenuity in some sense? So in the same way as Turing said, that's not the case. I mean, you definitely cannot solve all decision problems in logic. And then as an extension, there are other simpler logics like the one we will talk about. And to address those, Bucci came up with this. But today, what we are looking at towards the second half I will talk about is how you then take this and talk about maybe more modern systems and how you verify. So what is a finite state automaton? The simplest way is to just draw you a picture. So it's a graph. Okay? There are states, and then there are edges, and the edges are labeled by actions. So it says that if you are in state S1, and you basically, if you're in state S1 and you take an A action, then you will go from S1 to S2. If you're here and you see a B, then you will go from. So these actions, these letters are abstractions of activities or actions. It could be, you can think of A as opening a web page and B as downloading a PDF file. So these are kind of some abstract atomic actions. And after it does something, it goes from this state to that state. Okay? So you have two special kind of things. You have to start the computation somewhere. Right? So that's what's called an initial state. So the initial state in my pictures will be like this. It will just be this incoming arrow coming from nowhere. So this says that every computation this automaton does is S1. starts in S1, and then there is a notion of whether or not the computation was successful. So there are some so-called final states, and if you end in a final state, then the computation succeeded. If you do not end in a final state, it did not succeed. Okay? So here the green colored thing, so S1 in this case, is a final state. Okay? So I will do an example and it will become clearer. So the way these automata work is they process an input. So what is an input? An input is just a sequence of actions over that alphabet. So we have a finite set sigma. In this case, it's just A and B. So you have a sequence A, B, A, B, B, A, or something. So let me just write a sequence. I'll write. So supposing I write a sequence, right? Like. So now what happens is that this thing will execute it. So it will start from here and it will see an A and it will go there. Okay. So now it has done this. Now it will see a B and it will stay here. And it will see another B and it will stay here again. So now these two are also done. Then it will see an A and it will come here. And then it will see a B and it will stay here. So at the end of this execution, it started in S1, went to S2, did a round in S2, came back to S1, did a round in S1, ended in S1. But S1 is green. So this input AB, B, AB is a good one as far as this one goes. So this sequence of following these edges along the input is what's called a run. And if the run ends in a green state, then it's called an accepting run. If it ends in a non-green state, so there could be more than one green state. There's only one place to start, but you could finish in more than one place. Here there's only a trivial thing, so it's only one place. But if you end in a good state, you accept. If you don't, then you reject. So what we are interested in is which words. So this becomes a kind of combinatorial question. So which words will it accept? So can you characterize them somehow? Right? And conversely, if you want to accept a certain set of words, how do you design an automaton which captures exactly that set? So that's usually how automata theory problems are phrased. Right? So in this case, can you figure out what happens?
Have even number of A's.
So you can see that when you do a B, it doesn't affect. B either keeps you here or keeps you here. So B does not change your state. What changes your state is A. So if you do one A, you go away, and if you do another A, you come back. So every alternate A brings you back. Every other odd A takes you out. Right. So this one is something that accepts any input which has an even number of A's, including 0. Zero is also. Okay. And this is so you have therefore with if I give you an automaton, there is a set of inputs. So each input for the moment is finite, right? But unbounded. So I could give you longer and I could give you something with 5,000 A's and 6,000 B's and something. Okay. So each input is either accepted or rejected, and the language is those things which are accepted. And the language could be empty. For instance, if I'm also allowed to have no green states, in which case, no matter what you do, you won't reach a green state and then you get stuck. Okay. So it could be empty, it could be everything. Everything is a green state. I could just have a simple automaton which just has one state which accepts everything. So all possibilities are there. Okay. So we are interested. So one of the questions is which subsets are described. If you think about it abstractly, the number of subsets is uncountable. Because you have the set of strings is countable and you have subsets of a countably infinite set. Okay, so the number of languages is uncountable, but I can enumerate automata. I can say state 1, state 2, H1, H2. So I can enumerate automata. So I only have countably many models and I have uncountably many languages. So it is very clear that there are some languages which cannot be. Okay, so these are the so-called regular languages, but we won't talk about it much. So one of the properties of this model, maybe you just want to, is that in the earlier thing, we assumed that this transition is unique. That is, if I'm in a state and I see a letter, I will always have one move and only one move. Okay? I will not have 0 moves, I will not have 2 moves. Now that can be relaxed. So this is what's called non-determinism. You could have any number of transitions for a given letter. So here, if you look at it, on this initially, if I'm here, right, if I do an A, I could either stay here or I could go here. Right? So I have 2 possibilities. And notice that if I am here, for instance, and if I see one more letter, I don't have any possibilities. So if I've already reached S3, then I should stay there and I should have finished my input because there is no outgoing thing for either A or B. So in this case, now you could have multiple the same input, I could, for example, if I give you AAB, then I could go AAB and finish, or I could go AAB and stay here. Right? So I could do more than one thing. Right? So in this model, among all the possible runs that you can do, if any one of them takes you to the good state, you accept. Right? So in the earlier case, AAB will get accepted because one of them goes like this. So this is sometimes called guessing. Right? So non-determinism is actually something which is one of those few concepts which did not really exist before automata theory or before computer science. So traditionally, people would think of this as a probabilistic. There's a probability of like a Markov check. I can go here with some probability, or I can go there with some probability. So there is a choice, but that choice is governed by some kind of external distribution. Here there is no distribution. Right? It's like you want to guess in advance what is the best thing, and if it is possible to guess a good thing, it will guess. Right? So it's quite kind of magical in that sense. And yeah, and as I said, if I give you, say, for instance, ABBA, right, and you start ambitiously by saying, okay, I'll go here on A, then I'll go here on B. So then at this point, you're already reached a state from which I cannot make another move and you're dead. Right? So that kind of a run is implicitly not accepted. Right? So you can either you don't accept because you reach something which is not a good green colored good state, or you get stuck. But if you can reach at all, then you will accept. Right? So this one is a little harder to figure out what it does. But what it really does is it guesses. It's like, I mean, have you seen these guys doing this slow cycling? This Olympics is always fascinating. They'll be going around this thing, this so-called sprint. Right? It's a so-called sprint, and they'll be going slower and slower and slower and slower. And at some point, one guy will make a dash. Right? And the idea is to time it so that because the guy behind has an advantage because he's in the wind shadow. So you have to time it so that you will reach the finish line before that guy's advantage takes over. So similarly here, but just as an analogy, you believe that the second last letter of your word is an A, so you wait for it, right? And at the right moment, you make a dash for it and finish. So if your second last letter is an A, there's always a way to do it. If your second last letter is not an A, you can think about it, there's no way to do it. Whenever you make this transition from left to right, there is going to be a problem. Either you will run out of letters because it was the last A, or it was third last or more, in which case you will run out of letters because of the next one. So this one accepts the second last letter. Now this is actually an interesting example because if you do this without this non-determinism, intuitively what you have to do is you have to remember whether the second last letter was an A. So you will accept if the second last letter you saw was an A, so you have to remember the last letter and the second last letter. And you keep moving, you shift it out. So the next letter you read, the second last letter goes off and the last letter becomes the second last letter. So you just remember the last two letters you read. So then you have, because there are two letters now, so you have a possibility that you only read one letter and then that you have read two letters. So you have some 7 states. So here you have 3 states. And it turns out that in general, you go from n states to 2 to the n states. Right? So this is something which is an early result of automata theory, which is that you can always go from a non-deterministic automaton to a deterministic automaton, but you pay a price. Right? You might have to remember more things to make your decisions, and it could actually be exponential. So this is as far as conventional automata go, but we are looking at slightly unconventional automata. Okay? So what Vicky said is, what do you do if now this sequence of inputs is not finite? Now, from Yuki's point of view, as I will explain, the motivation was different. But from today's point of view, it is quite, yeah, it's okay, don't worry, I saw it anyway. So, from today's point of view, the thing is that then it will become noisy. But, see, again, going back to this, right? See, if I write a program to compute square root and if it goes on forever, it's a disaster. Right? That something's wrong. But if my phone reboots, that's a disaster. Right? So this phone in principle should never be rebooted. Right? Or my laptop or my desktop or anything which. So actually we are hypothetically trying to describe infinite computations in the context of such servers and these kind of interactions. So it makes a lot of sense to think about infinite sequences of actions from the verification perspective. But Bucky's point was logic, which I will explain. So the first problem with infinite thing is there is no end. So our earlier definition said when you reach the final state, you will be in a green state and you will stop and decide whether it's green or black and so on. But there is no stop. Right? So how do you decide? So you keep the picture the same. Okay, this is what Bucky proposed. So this was his model, invented by him. He said you keep the picture the same, but now you just change the interpretation of the green because you're never going to stop in the green. But what he wants is that you go through the green state infinitely often. So if you are processing infinitely many letters, you must see a green state infinitely often. So that's because you can't stop there, but at least you will not avoid it from some point on. Okay. So this one, for instance, right? It's actually the same. If you remember, this is very similar to that even thing, but it's slightly different. So what this has done is that if I I want to see this state infinitely often. So this is the green state. Okay. So how can I get to the green state? The only way I can get to the green state is by following this or this. So these are the only two incoming arrows taking me to a green state, but both of them are labeled A. And the other arrows take me away from that and they're labeled B. So in a sense, every time I see a B, I go away from the green state. Every time I see an A, I go towards the green state. And I want to see the green state infinitely often. So I must see an A infinitely. It doesn't matter whether I see a few B's or lots of B's. I can do alternately AB, AB, AB infinitely many times. That's fine. I can do all A's. That's also fine. I can do 3 B's and a lot of A's. That's also fine. But I must see an infinite number of B's. Okay? So that is the language that this one describes. Notice that this is deterministic. If I'm here, there is an A out and a B here. If I'm here, there is an A out and a B here. So each of them has exactly one A and B pointing out of every state. So at every point, the next move is uniquely determined by what letter is. So here is a no. So it's like this. This one is. So now what happens is that in order to reach a green state, okay, infinitely often, the only thing that takes you there infinitely often is the B because the A comes only once. So there is some point beyond which you'll see only B's. So if there is a point beyond which you see only B's, then the A's are over. Either there were no A's or there are a few A's. So at some point you see the last A, and on the last A you move to the green state and you stay. So till then you can do so on this at this initial thing you can see both A's and B's and just keep processing without changing it. But on the last A you move. So this actually describes the complement of the previous one, right? So in this point you have only finitely many A's. The previous one said there are infinitely many A's. So these two languages are the complement.
If there are no A's, then will not end up in the green.
So actually, yeah, technically, if there are no A's, then you have an issue. Right? So
I think the middle array you can put A, comma B then.
yeah. Good point. For 0 A's, you need some way to get there, so you can move on to first. Right, so this is the complement of the previous language. Okay, but this one we designed it. We designed it with non-determinism, and in the finite case, we claimed that non-determinism can be eliminated. Okay, but here, unfortunately, it cannot. Right? So there is no deterministic automata. This is something that we proved. So this means that for this class of automata, the model is not easy to complement. I mean, I cannot take a language. So it turns out, and this I see the usual way that for the other class of language, I said the thing is that which subsets of words are recognized by an automaton. So now if you have a deterministic automaton, you can only do one thing, right? Then wherever it was good, you make it bad, and wherever it was bad, you make it good, right? So there's only one way you can process an input. So if your old automaton accepted a word, you reject it. Your old automaton rejected a word, you accept it. And for that, you just have to swap the green states and the black states, which is green, which is black. You will automatically accept the complement language. Everything that was rejected by the first case, accepted by the second case, vice versa. So if you have a deterministic model, it's very easy to argue that the set of languages is closed under complementation, because I just have to take the model for one language and flip the interpretation. But now this theorem says that this is not, I mean, this counter example says this is not possible, right? So in this case, deterministic automata cannot capture all the language. You need non-deterministic automata. And if you need non-deterministic automata, then that trick doesn't work anymore. Because both of them, I mean, I could have a lot of runs which reject and one run which accepts. So if I start flipping states, it's not going to have the same interpretation, right? So it's a non-trivial thing to show that this, after this infinite extension, that still the languages are closed under. But this is true, right? So it does satisfy these Boolean properties. It's closed under union and intersection. Union and intersection are not very difficult. They are very standard. Like although you have to be a little careful about intersection because you have to check that they go through this set of green states infinitely often and that set of green states infinitely often. So it's a little bit of hard work. But complementation is very non-trivial. And this was Yuki's main result when he first proved this. Right? And the other thing that you can do is something called projection. So let me just describe it. So the first thing says that if I give you two automata A1 and A2, each has a language L of A1 and L of A2, I can effectively construct an automaton which is L of A1 union L of A2. Okay, the second one says I can do the complement, but complement with respect to, so earlier I had used this notation for finite sequences. So now we are talking with respect to infinite sequences. So this is normally written. So these are infinite sequences. So all the infinite sequences which are not in the language of A prime, I can construct an automaton to recognize that. And that is non-trivial because it's not necessarily deterministic. And the last thing is that if I take this alphabet and I erase some letters, right? If I take an alphabet with 7 letters and I say 4 of them I don't want, I just look at the strings I get by compressing it to 3 letters. Right? Then I want to know that whether the 3-letter projection corresponds to a word which with 7 letters was accepted. And that you can show. Right? So it is closed under projection. So that is one part of it, which is to do with arguing that these automata have this nice property of being closed under Boolean operations. And that will be useful because in the end, we are going to connect it to logic. And in logic, formulas are constructed using these things, and not. And the projection corresponds to quantification. There exists. So if you can show that there is an automata operation for each of these things, then you can do an inductive construction, saying that if I combine 2 formulas and I have an automaton for the 2 formulas, I can combine the automata to get an okay. But finally, what do we want to know? We want to know whether or not this formula, what is the status of this formula? Can this formula be made true or not? Okay. And that it will turn out in the automata theoretic sense that what it turns out is asking whether the language of the corresponding automata is empty or not. So this is a fundamental question that you want to ask in any automaton model. Does it accept anything at all? Is it a non-trivial automaton? Does it have at least one accepted string? Okay. So in the original model, the finite model, it's actually just a graph reachability question. You have a green state, you have a state which has got an incoming arrow, it's a starting state. You just want to know in the graph whether there's a path from there. So reachability is just the non-emptiness is just a simple graph reachability question on a finite graph. Here you have a finite graph, but you have a more elaborate notion that is that you must get to the green state and then you must keep coming back to the green state. Okay, but that's not also very difficult. It just means that you follow this kind of a thing, you get to a green state. So first of all, if in principle you could be visiting any green state infinitely often, so there could be 3 green states, G1, G2, G3, and together they are visited infinitely often. but there are only finite number of them. So if together they are visited infinitely often, at least one of them must be visited infinitely often. So you can throw away the other. So you can focus on that one state which is visited, at least one state is visited infinitely often, and say, okay, I reach it, and then I keep coming back. Okay, and this now is a graph theoretic property. Is there a G which is reachable from the starting state, such that from G I can come back to G? If so, then there's at least one input which can follow that trajectory. I just want to know if there is any input I can accept or not. I'm not concerned about which input it is. I just want to know, is there a path which can accept? Okay? So this becomes decided. So you just have to check if some final state is reachable with the loop back to itself. So for this model now, what I have claimed is that it is closed under these Boolean operations. And this emptiness, language emptiness can be effectively checked. So if I draw the automaton for you, you can figure out whether or not it accepts at least one input, infinite input sequence. Okay, so now why was BP doing this? Because he was interested in proving something about what he called the logic of sequences. Okay. So this is a logic which is interpreted over a fixed domain, which is the natural numbers. Okay. So I have had this problem when I talk to various people in school and all that. So in computer science, natural numbers always start with 0. So when I say natural numbers, I mean 0, 1, 2, 3. So the logic has the numbers, okay, but it doesn't have arithmetic. It only has successor. You can say successor of 1 is 2, successor of 7 is 8. Okay? So there is a function which maps x to x plus 1. That's the only function that is there on these numbers. So mathematically, it's a set of natural numbers with plus 1. And now you can quantify, and the interesting thing is you can quantify over not just the usual quantification. When we say in mathematics, we say for all x, something we usually mean that x is a member of the object structure that it's a member of the norm or the ring. Here you can say for all capital X, for all subsets of. So this is called, so for that reason, this takes us, that subset part takes us into what is called second order logic. Okay, first order logic, the quantifications over individuals. Second order logic, the quantifications over higher things like sets and functions and relations and so on. But we are not allowing quantification over sets and functions, but only subsets. And a subset is, if you think about it, a subset is a unary relation. Okay? A subset can be thought of as a relation of one, those which are there and those which are not there. Right? So it's just so what is the relation? R is a subset of x cross y. Now we only have x. So R is a subset of x. So it's just a unary relation. So that is called monadic. Okay? So it's a monadic second order. So it's a very restricted form of second order with one successor. So that's why it's called S1. Monadic second order logic of one successor. One successor because I only have one successor, like 1 goes to 2. If I have 2 successors, then I have a tree. There's something which has left and right, left and right, left and right. This logic extends to the tree, but that's an extremely non-trivial thing. Okay, it took another 10 years to prove that, and that's really at the boundary of what is decidable in terms of. But anyway, we're not going to talk about 2 successors, only one successor. Okay? So what is this logic formally? You only have one constant 0, right? And you can write successor of 0. You can write so successor of 0 is just another way of saying 1. So if any of you have ever seen things like set theory and foundations of mathematics, they'll always start with empty set is 0, and then the set n is the set containing n minus 1. Right? So you just build up by adding one more level of nesting. So here you add up by just applying successor. So 2 would be, for example, successors. So you don't need any more. You can write 1, 7, any finite number you can write in your formula, but it really means successor of successor of successor that many times or 0. Right? So the formal syntax only has 0 and successor. And then you do the usual thing. You first use Boolean things. So you can say not or and. So you can combine formulas. I'll show you an example or two so that you can see it. And then you can do this quantification, right? You can say there exists a for all, but you can now, if I say small x, small y, I mean a number. If I say capital X, capital Y, I mean a subset of numbers. So I'll show you an example. And then you can ask, because you have sets and elements, you can write a formula which says small x belongs to capital X. is true if the current interpretation of the model is true. Then you can ask whether so a formula is now supposed to represent some collection of things. So is this collection equal to that collection? So is this term equal to that? So with this, you can define a claim subset. Right? So notice that we don't have subset, we only have element of. Now, what does it mean for a subset? X is a subset of Y, if everything that belongs to X also belongs to Y. Right? So you just say that for every small x, if X belongs to X, then X belongs to Y. So this would mean that the input capital X and capital Y, which are sets, are actually in the relationship subset. Right? So this is the kind of the way in which you build up. So now you can start using subset because subset is definable in the logic. You can define order. See, you only have +1 and you don't have transitivity. Okay, so transitivity is not built into your logic. But you can define the effect of transitivity by saying that, so I want to say that X sitting below Y, okay? And I'm saying strict. You can modify it to be less than equal to. So what you want to say is that if I take the next position, okay, and then I saturate by taking the successor of everything, then I cannot avoid Y. And that's what this thing. For every set Z, which contains X plus 1, and which is saturated, that is, for every element in Z, the successor of that element is also in Z. If I have any set of this form, which contains the successor of X and is saturated with successor, Y must belong to that set. Okay. So this is only true if Y is to the right of Z. If Y is to the left of X, I can have a set like this, which does not. Right? So you can express X as that. Now this is probably the most interesting question that you can. So you can actually describe induction in this way. So this says that any set which contains 0, right, and which is saturated. This part is the same as above. For every X in X successor, any set which contains 0 and is saturated must contain everything. So this is what induction says. Right? Induction says you establish a base case and you show that for some, if the property holds for n minus 1 or n, whatever it holds for n or n plus 1. Therefore, the property holds for all. Okay? So that's what this is saying. Of course, this is in a very limited setting in this context, but you can actually say very non-trivial things in this context. So the question now, which Yuki was trying to answer is, if I write a formula like this, like in principle, I could ask, is that formula for induction, is it true or not? Okay. So is it actually a valid? So the question is one of satisfiability. So I give you a formula which has some variables. You are allowed to say X is 7, Y is 22, capital X is 3, 4, 5. You can put any assignment that you want for these variables. Right? And under that interpretation, this formula will be either true or false. So the question is, find me an interpretation. This is satisfiability. So in the Boolean case, we just have a formula P1 or P2 or P3, and we say set each one of these variables to true or false and tell me if the formula as a whole is true or false. Here I have to take each one of these variables and assign it either to a number or a set of numbers. And with respect to that interpretation, so it's of course a much larger universe of possibilities. In a Boolean formula, it's a finite formula. There are only so many variables, and there are only 2 to that many things, so I can exhaustively check. But here it's not possible because there are infinitely many possible ways of mapping each variable to a number or to a set of numbers. Right? So there's no direct brute force way of checking this. So can we find an assignment? This is the question. Okay. So to connect it to Automata, what Yuki said is that he will think of sets as strings. So remember that before this we were talking about words over some AB and all that, and then we moved to this logic over this 0, 1, 2, 3, 4. So now he's going to connect the two. So he says that you think of any set, so I can just think of the entire set of natural numbers and I can mark out the elements that belong to the set. So the characteristics. So this is in the set, this is not in the set, this is in the set, this is not in the set. So whichever elements belong to the set, and in particular, an individual variable is only a set of size, it's the same as a set of size 1. So I can think of a small x, right, as a set which has only one position marked, the value of that variable. And if it's a non-trivial set, it will have many positions. So this is just a characteristic function. For every x, every position in the sequence. So now implicitly the sequence, this is the insight. I give you an infinite word. The positions in the sequence are 0, 1, 2, 3, 4. So I think of them as a number 0, 1, 2, 3, 4, and I tell you which positions are in my sequence. Right? So by just using the fact that the positions in an infinite word are actually the natural numbers, I can now make this condition. So I give you I can write out this characteristic function. What is the value at 0? What is the value at 1? So is 1 in my thing? Is 2 in my thing? Right? So for example, if I want the set which consists of only the odd numbers, right? At all the even positions, it will have 0. At all the odd positions, it will have 1. Right? So this infinite word 0, 1, 0, 1, 0, 1 is equivalent to the set 1, 3, 5, 7, 9. Similarly, this is equivalent to the set 0, 1, 4, 9, 16, 25, the set of perfect squares, because I just put 1 at exactly those positions which correspond to perfect squares. Right? So this is the thing. So I can take any. So what I'm looking for is these kind of assignments, right? So an assignment is mapping that to a certain subset of numbers, but I can represent that assignment through an infinite sequence. So I can connect it back to this idea of automata. So what we will do is that we will, if I want to check whether two sets, for example, I wrote that less than, right? Less than of m comma n, I had given you, it takes two input sets. So I will replace m by the sequence representing m. So I will think of it as a 0, 1 sequence. I will think of n as a 0, 1 sequence. So this is what I call sigma x and sigma y. And I will run my automaton on these two sequences and check whether these two sequences validate less than. And I will show you an example with less than. So here is, supposing I want to check whether two given sets m and n validate less than. So first of all, less than is a property of two numbers. It's not a property of two sets. It doesn't really make very much sense to say a set of numbers is less than another set of numbers. It's normal convention. So these sets must both be singletons. That's the first thing. Right? So if I look at the sigma n and sigma n, they must have exactly 1, 1. All the positions must be 0 except for the number small m and small n. That's one property. And the other property is that the one in the first sequence must appear before the one in the second sequence, because it is less than. So wherever x capital M is, it's one, it has only one by the first student. It must appear before the second. So what I'm looking for is an input. So what this automaton will do is it will actually scan this. There are two infinite sequences, one infinite sequence for capital M, the top row, and one for the bottom row for M. It will scan it to one pair at a time. It will look at position 0 at both, position 1 at both. Okay? And the good case is something like this, where at all but two positions, both of them say 0. Right? And the position where the first one says 1 is to the left of the position where the second one says 1. So there will be exactly two entries of the form 0, 1, 1, 0. And the 1, 0 must come before the 0. So this is what it means for these conditions to be. And this can be checked by an automaton. Okay. So here is the automaton that does that. Right? It just starts and it keeps ignoring 0, 0. 0, 0 is a safe thing, but it doesn't tell it anything. Then it ensures that the first thing that is seen, which is not of the form 0, 0, is of the form 1, 0. It must look like this. It should not look the other way. Okay? And it should not be 1, 1 also. 1, 1 is also possible, that m is actually equal to n. Okay? Having done that, you can again skip arbitrarily many positions because it is less than. Then you must see the other corresponding one saying that now I have seen n. Because if you've just seen m and not seen n, it's not good. And once you've seen both of these, then you can proceed as long as you don't see any more. So it's doing a lot of things, right? All the missing edges are taking care of all the things that you don't want to see. You don't want to see 1, 1 anyway. So there's never a transition of 1, 1. Right? And you don't want to see 0, 1 before 1, 0. You don't want to see anything after the last thing and so on. So all those things will make it get stuck. So if I see any input which does not have that format, it will get stuck. So it will accept precisely when it has that format. But within that format, it doesn't care where it is. It can see that 10 and 01 anyway. So that is this non-trivial thing about this, that this automaton in one shot will accept any valid MNN. It's not a particular MNN. If you look at the language of this automaton, every input sequence that this language accepts, this automaton accepts, will have an interpretation as m less than n. And every m less than n will be accepted. Okay? So in that way, this automaton captures that formula. The language of this automaton is precisely all the satisfying assignments of that formula. Whenever you can satisfy the formula, the corresponding string will be, or the sequence will be here. And whenever the sequence is accepted, it will be interpretable as an assignment. Right? So now we come to this idea. What is the question? The question is satisfiability. Right? So if this automaton which I have constructed, which has this universal property with respect to these satisfying assignments, if there is an assignment at all, this must accept it. So the only way that that formula cannot be satisfied is this automaton doesn't accept it. Right? So that's where this non-emptiness comes in. I construct the automaton from the formula, and then I check, can this formula actually, this automaton actually accept something? It's equivalent to answering the question of whether the formula could actually be made. Right? So this is the strategy that basically Buki now came up with. So he says, so for every formula in this S1S, monadic second order logic, you can construct an automaton, right? And how do you construct the automaton? You construct it by induction because you have an operation for every operation in the formula side. On the formula side, you have not, you have complementation of. On the formula side, you have or and you have union and intersection. You have the existential quantification, and you have this projection operation which corresponds to. So I won't get into why it corresponds to, but projection that suppressing, which basically means that you're suppressing one row. When I say there exists an X, you're saying that construct a row for X and then throw it away. Like construct a row for X, but it's not actually part of my input. I must manufacture an X such that something goes. So that comes down to projection. So then, as I said, now you have the property that this automaton accepts precisely those inputs which correspond to valid satisfying inputs for the formula. So if the language is empty, then the formula cannot be satisfied. The language is not empty, the formula has a satisfying. So you have solved the decision. And we know that we can, that lollipop thing I showed you. So there is an algorithm to check this. So once you've constructed the automaton, checking whether it's empty or not is true. So actually from this, what Buki concluded, so I discovered today that there are 2 years. So 1960 is when the paper was actually, when the result was announced, but 1962 seems to be when it was actually published in proceedings. But he basically said that these two are the same. So that the languages you can describe using this second order logic, and the languages that you can describe using these automata. And then there has been a lot of work since then on finding different automata which are slightly easier to work with than these. But this has been the cornerstone of this area of research. Okay, so now I'm going to slightly, last 15 minutes or so, switch gears and talk about this verification thing. Right? So this was a purely exercise in logic. If you wanted to show something about the stability of some abstract logic over sequences, and he was able to connect it to automata and show that operations on automata give you the result that you want on the logic.
Typically, one language does only finitely many automata exist, or there are cases like infinitely many automata can exist.
Infinitely many, I mean, there are infinitely many automata exist. So what is the question? Because I can draw larger and larger with many more states. But and also the set of the class of languages will also be infinite. But because the automata are enumerable, I can enumerate the automata. I can take all automata of size 1 with 1 state, all automata of 2 states, all automata of 3 states. So I can write them out. So clearly, the class of automata is countable. So therefore, the set of the different number of subsets you can define, and therefore different number of languages
can have some different branches, like one kind of one is not contained in the others, kind of not comparable. Kind of.
So with this particular class of automata, I think there is, because they're closed under union and intersection. So you will have some kind of, in the language level, you will have some kind of lattice property. If the two things are there, the union will be there and the intersection will be there. But I think there are other more elaborate classes which go beyond this. Okay, so coming back to now this more applied question. Okay, so the question is one of verifying that some program or computer system or whatever that you've built is doing what it's supposed to do. Okay, so this is broadly what is called verification. So if I give you a classical program, it takes an x and produces f of x. So your validation consists of somehow establishing that every time you feed an x, you will get f of x. Okay? Now, of course, at the most trivial level, one way is to just test it on a lot of inputs and convince yourself that it passed 100 tests. But otherwise, you might look at the logic of the program and say, okay, this, and therefore I have done this. But this is a 1:1 mapping. Okay? So what I was saying earlier is that there is a large class of systems which we are currently more interested in. Okay? So there are schedulers and anything to do with the communication system, any mobile tower or anything, operating systems that run our devices. Right? All of these things don't compute in that sense. So what happens is that I press some button on the screen and something happens. So it's waiting. Most of the time it's just waiting for something to happen. Right? So there's an environment. So as far as the phone is concerned, I am the environment. Right? So it's just sitting there waiting. So I am the environment. The cell phone network is the environment. So if some call comes from outside, it's like somebody is contacting it. If I'm pressing something, okay, so that's the kind of system that we have. And then it's supposed to do something appropriate based on what the stimulus is. If it's an incoming call, it should ring, unless it's on silent, in which case it should not ring, and so on. Right? It could be in different states. So these have sometimes been called reactive systems because they are really designed not to compute outputs from inputs, but to react to these kind of interactions. Okay? And for this, the question is quite different as to asking when is it correct, because I have to talk about the sequence of interactions. So now that becomes so we've been talking about sequences, right? So in principle, the sequence of interactions is unbounded. So I would like to say that if I press some app icon now, then at some later time that app will open. Right? May not happen instantly, it may happen a little later, but so if I press 5 buttons, hopefully all 5 of them will open. Right? So these are the kinds of things I want to talk about, something that happened now and something that happened later, or some promise or something like that. So here is one typical computer science motivating example. So if supposing you're in a place like KSOM or any environment, so usually there is a shared printer. Right? So if you print and somebody else prints, right, clearly something has to be done to ensure that the pages don't get mixed up. I mean, the data on a page at least should not get mixed up, but the pages themselves should not get mixed up. So there should be some coordination. Okay? So here's a kind of stupid thing. You don't have to worry about it, but this is the kind of thing that maybe there are 2 different. So each laptop typically runs a print server on its own. So it's trying to contact the printer. Right? So it will go through a thing where it's just sitting there in its doing nothing, and then you press print on something in your application. So then it tries to push something to the printer, but it has to coordinate with the printer and the other people to make sure that 2 printouts don't happen. When it gets permission to, it will print, and then it will go back and become. Because in the meantime, you could have given a second print job, in which case it starts a cycle. So now if you have one laptop or one server which is doing this, right? There could be somebody else who's doing the same thing on their laptop. Okay? And now we want to guarantee something as a whole about this thing, that the printer never ends up printing at the same time from both of these servers. That's a very limited but minimal expectation. So if I want to analyze this, the standard way is I have to look at this thing as a parallel system, and I have to kind of draw this kind of a graph, which says, okay, initially they are both idle, right? And then say this one moves. So then this one is waiting and this one is idle, or this one moves. Okay? So each one of them will make a move, and then correspondingly in the global representation, one of the states will change and the other state will not change. And what do I not want? I don't want. So this, I don't want to see this. So this is one of the ways in which this verification proceeds in this automata theoretic setting. So in this thing now, remember the point is it's not a function of one execution, but of the continued execution. So I have to really think about these infinite executions running through this graph and say that none of them, so here it's very easy by inspection to show you that that state is not there. But in general, you have to check that certain bad things or certain good things don't happen. And now we come back to this problem that I started with, which is how do you say these things, right? How do you say that, for example, that they don't both try to print at the same time? Right? That's what's called mutual exclusion. Or how do you say that all the printouts will actually come? Right? I press print and then I'm willing to accept that it'll take time. I go and have my chai and come back. Some point it must come. Right? And it should come in the sense that it should not then suddenly say it has happened and then you go and there's no printout. It's just been swallowed, which happens to like complaint requests that you give to EB or something like that. Right? So that should not happen. So you need to make sure that these kind of things can be described and then validated. Okay? So it actually turns out that we could have done this in S1S. Okay? The S1S itself is powerful enough because we can talk about less than, we can say after this something else must happen and so on. Okay? So we can attach some few more predicates to our logic and do it. Okay? But unfortunately, one of the problems with this S1S is that computationally it's known to be a very expensive logic. In principle, I talked about right at the beginning that when you take the deterministic, the original automata, and you go from non-deterministic to deterministic, you pay a price of exponential. So it turns out in these automata, every time you complement, you pay a price over exponential. And that price keeps getting added. So in general, I could give you a formula which is of size n, and it could take 2 to the 2 to the 2 to the 2, a tower of exponentials whose height is proportional. Right? So in principle, these are very large automata, and hence that whole business about checking the emptiness and all that is proportional to how many states you have to explore. Now, actually, people have shown that, as with many of these hardness research, that these are very rare situations, and actually, in practice, it works. But still, there was a motivation to ask whether you really need S1S or not. Okay?
How one decides this is a rare situation?
You can't. So it's like, I mean, if you are familiar with this NP completeness theory, right? It's trying to argue that. Right? So it is not that we are not solving scheduling problems left, right, and center. But the point is that hypothetically there are very bad inputs, but they are always, in some sense, they are always artificially constructed inputs which are designed to be adversarially bad. But if I give you any practical input, it seems to work. So in that same setting, you just try it and a few times it will fail. But say 99% of the time it will work. So then that's better than saying I don't have anything. So in that sense, but no, it's very hard to characterize. If you knew that, then you would be a lot, theoretically you could do a lot. So there is a simpler logic which I'll just briefly describe called temporal logic, which is actually a sub-logic of S1S. Okay. So in temporal logic, you start with some, so if you ever studied Boolean formulas in college or something, you have this atomic fact, the grass is green, sky is blue. So you assume there are all these things which are either true or false, and then you start combining them. So when you say P or Q, P and Q, those three Qs are basically these atomic assertions, and then you don't further question after that what they mean. So similarly here, there are some assertions about this thing which I may be interested in, right? I may be interested in the state. Server 1 is idle, server 2 is waiting. So which state there? So these are assertions about the system, which I can then plug in as these symbols. Okay? And then I can ask, is server 1 idle and server 2 is printing? Or is server 1 idle and server 2 is not printing? So I can combine these assertions using Boolean formulas. Right? And now I'm not going to allow quantification like I did for second order. Instead, I'm going to talk about positions the sequence. So I can say that, is it the case that server 1 is idle now, and in the next state, the server 1 is waiting? Or is it the case that server 1 is waiting now, and sometime in the future, it is printing? So we have these formulas which are called next henceforth, that is from now onwards, and eventually sometime in the future.
This is like the less than thing that you would.
Yeah, so less than would be like the last one, eventually. It says that there is a future position. Henceforth means everything from now onwards to infinity. So one thing I want to say is that henceforth, I never see print 1 and print 2. So that is a thing that I want to guarantee for it. Whereas the last one would be something like if I give a request now, I would like the printout to appear later. So there is something. So these are pictorially the interpretation. So if I assert next step here, it is true if f is true at the next sequence. Okay? If I say henceforth, then it means that all the way and forever is, and eventually means that if I assert it here, then there is some future quantum. Okay? And now we can start writing these things. So the reason you want to do this is because you want to describe those informal problems. Right? So for example, mutually exclusive says, as I said just a minute before, henceforth, and so remember these are right, I1, I2, W1, W2, P1. These are basic assertions about the system. So I never want to see P1 and P2. So henceforth, P1 and P2 should be negated. I should never see P1 and P2. This says that I never have the printer being simultaneously accessible. Or I can say that every print request is granted. So henceforth, if I see process 1 waiting, then eventually it will print. If I see process 2 waiting, so wherever in the future process 1 makes a request or the first server makes a request for printout, it will eventually get it. Every time the second server gets it, will eventually get it. And then there are some more abstract things. So this says that at some point the property stabilizes. So there are some systems which initially have some unpredictable behavior, but then they will settle down. Right? So this is called stability. So eventually some property f becomes universally true. And this is more complicated. It says henceforth eventually f. So what this says is that I sit here. So henceforth eventually f. That means every point in the future eventually f is true. So in particular at some point I can see f. Because here also eventually f is true. But at every point this is true. So here also henceforth eventually f is true. So I must see one more f. So every time I see an f, this henceforth says that from that point again eventually f is true. So this actually means that f will happen infinitely. So these are the kinds of things that you can do. Now there is a subtlety here. When I said before that waiting implies printing, it could be waiting, printing. Okay? It just says that in the future of a W1 there is a P1. It doesn't say that in between it didn't go back, lose it, and then come back to W1. So what I would really like to say is that if W1 is there, then it will remain W1 until P1. Right? So that requires something strong.
Go back to idle and then.
Yeah. So you want to actually persist with something until, so you have a promise, but until the promise is fulfilled, you have promised something will continue to fulfill. Okay? So that is this thing called until. So you have you're waiting for G to happen, but until G happens, F is invariantly true. Right? And this is really what you want to say. You want to say that if I wait, if server 1 waits, then server 1 will wait until it prints. So the until promises you the eventually, because there must be a point where you print. And before that, you're not going to get chucked out. That's what it means. So this is this temporal logic, right? And now you want to ask the same thing, right? So you set up your temporal logic formula and you want to check whether a system satisfies these things or not. So what it means to satisfy is basically to satisfy from the starting position, right? So you must look at every execution and check in every execution the formula that you want is true at the starting position. So this is what is called model checking. So model checking basically says, give me a system that is that automaton description of your thing and give me a temporal logic formula in this case. It could be any formula, but we are talking about temporal logic. Give me a procedure to determine whether S satisfies F. Okay? And it turns out that there is a more, you can of course, as I will tell you in a minute, you can actually translate this into S1S and go via Yuki's result, but there's a more direct translation. You can build a more effective Yuki automaton for this and do exactly the same thing as before. Okay? So you take a formula and you build a Yuki automaton, it captures every execution that satisfies that formula, just like we did before for that S1S. It captured every satisfying assignment. And now you want to check whether the input system S implies, so from the input system, you can also think of it as an automaton. And then you want to check whether every execution of the system is a valid execution for the formula, which is just asking in terms of languages, whatever my system can do is included in whatever the formula is. So you are saying that this is the language of my system. This is the language of my formula. So it's a subset. So it should not go out here. Right? It should not produce a behavior which my formula declares to be false. Now, this is not technically a problem that you can solve, but you can do it the other way. Right? You can check that. Then, if I think about the complement of the formula, that's here. That language is disjoint from my system. So my system does not perform anything invalid. So there is no execution of a system which satisfies not if. So I can actually, since formulas are closed under negation, if I can construct for f, I can construct for not if. So I construct a formula for not if, an automaton for not if, and I check whether that is disjoint from this, and that is easy. That's just checking whether the intersection is empty. Intersection I can do, emptiness. Right? So this can be solved effectively. And the advantage of this is that it is a more efficient translation. It's only one exponential, not a tower of exponentials. So it's not really great, but it's much better than S1S. And from a theoretical perspective, what temporal logic actually turns out to be is that second order logic minus the second. If you don't allow quantification over subsets, okay, then you get this. Okay, so that's basically what I wanted to tell you. So I wanted to just give you a historical perspective, more or less, on this connection between logic, automata, and the way that this is applied in the context of model checking, which is where to solve this verification of systems problem. So just as a two-line thing to justify the title of the conference. So what are people doing now, right? So the thing is that we have made a lot of assumptions to make this fit, and the main thing is we have somehow made our systems describable as finite state automata. So what is the state of an automata? It is all the possible interesting things that the automaton is doing. Right? So theoretically, everything in the world is finite state, because the very fact that I can shut down my laptop and put it in my bag and open it later on means that uninterrupted, means that whatever it was doing, I could write it. That's what actually happens. Right? Somewhere on it remembers what you were doing. And even if you're downloading something, you have to start downloading it from there. Right? So all systems in reality are finite state. But hypothetically, they are not, because in principle, you could have more memory, more disk. So if the state depends on how much of data is there. So if you're talking now about values of variables and so on, and asking over that domain, or you're asking about time, like this printer, if you're saying not eventually, but will it be done in 5 minutes? This is the kind of problem that ISRO and these people have, right? So you can't wait forever. So if you give a command to your satellite or your nuclear power plant to shut it down, then it must promise you that in a certain amount of time it's going to shut down. Then you start reasoning over a domain which is not finite. So the so-called infinite state systems is really one of the big challenges, and how to bring in also these continuous things like temperature and time, and because typically computer science is very good at discrete things. Even values of variables are usually abstracted away as integers. But if you start using continuous values, and the other problem is just the computational complexity of this, because I showed you that. See, this picture already gives you a hint. See, if you combine two systems, then you get a new system which is a cross product of the two, right? And right, so you start with two systems and you get something which is a product of the two. If I give a third system, it will be, say, 3 times 3 times 3. So if I give you k components, then the number of states I get is to the power of k. Right? So this is what is called state explosion. So state explosion means that I need some effective way to deal with that, right? So how do I actually, so sometimes you can use symmetry. A lot of these components are the same. So if I can reason about 3, it will also work for 10. And so if I can say that 2 servers communicating on this protocol will not mix up their printouts, then any number of servers communicating. So that is one approach. So the people have looked for. So that is where things are. So I'll just maybe I'll send that. There are some survey things on this. If you're interested to get started on reading about this. Let's stop there. Thanks.
Any questions? Comments?
Clarification. You said at some point in your lecture that there exists no automata for this deterministic automata for something. So do you mean there exists no automata because previously you said every non-deterministic automata?
Yeah, so when it's finite inputs, it's always possible. In an infinite input case, you can prove some property of this thing which shows that if there was a deterministic automaton for this, then in the limit it would accept an illegal string. So the particular example was finitely many A's. So the deterministic automaton, if there was a deterministic automaton accepting finitely many A's, it will accept longer and longer inputs with finitely many A's. And that will force it to accept one input with infinitely many A's. Or something. So that's why you should.
Any other question from on the online?